Hi, it's the last day of July in 2019. I hope your summer is going well. A few days ago, I posted the next section of my online textbook, Visual Linear Algebra Online, at my blog, Infinity is Really Big. Section 1.9 is about the inverse matrix of a linear transformation. There is one main visual in this particular section at the very end of the section. For the most part, the content is very technical, a lot of computations, a lot of writing, a lot of explanations. It's pretty hard to understand, but it's really important. If you want to understand inverse functions and inverse linear transformations and inverse matrices, you got to work through it. So definitely take the time to do so. As usual, I'll give big overviews of things as well as subtle details. However, because it's kind of a long section, I need to sort of omit some details, I think, in order to get through this in a reasonable amount of time. At the very beginning of this section, I talk about inverse functions in general, and I do an example. And I emphasize that inverse functions are what you might call kind of a high technology in math. It's not that we're necessarily using computers to talk about inverse functions, but it's that they're very powerful. They can help you solve infinitely many problems at once, and that's a pretty amazing thing, actually. And I start with a nonlinear algebra example where we're looking at the height of a falling object as a function of time. Maybe this is a rock, okay, because we're not taking air resistance into account. H is in meters and T is in seconds. H is a function of T. It's 490 meters. That's the height at time zero. It's way up there. You're dropping it, letting it fall down. As a function of time, it would have this equation if there was no air resistance. And that is a function whose graph is a parabola, but we're only looking at a limited domain of this function, which does make the function one-to-one over this domain, and it does end up having an inverse function. If we were looking at it over a wider domain, it would not have an inverse function because it would fail the horizontal line test. Okay, so I talk about that, and I talk about solving, for example, for the height in terms of time for a particular height. How long will it take, for example, to reach 100 meters? This is the height as a function of time. It's not the distance fallen as a function of time. How long is it going to take to get down to 100 meters? Just do the algebra to solve for t and you find it's about 8.9 seconds. But then I say, what if we wanted to solve this problem for an arbitrary height? We could do the same steps, but you don't get a number for the answer, you get a function. T equals square root of 490 minus h over 4.9. That, in fact, is the inverse function in this situation. It does represent the answer for all possible values of the height between 0 and 490. Okay, it's a solution to infinitely many problems. Now, when you've learned about inverse functions in the past, you may have had a teacher or textbook tell you that in general you want to swap the variables at the end, like the y and the x around. And you might have wondered, why do we do that? Maybe you were told just because we like to have x as the independent variable. Maybe it was emphasized that if we graph them on the same set of axes, that the function and its inverse will have graphs that are reflections of each other across the 45-degree line through the origin. And that's certainly nice and true in that abstract situation, but if your variables mean something like they do in this case, h is a height in meters and t is time in seconds, you should not swap the variables. I can't emphasize that enough. So that's definitely, you want to keep the t as the dependent variable for the inverse function here and h is the independent variable. If you want to graph this inverse function, you should not graph it on the same axes, at least if you want to keep the horizontal axis as your independent variable. But you can swap the axes, and that's what I did down here. Okay. Now the fact that the original graph was decreasing and concave down is reflecting the fact that the object is falling and in fact getting faster and faster, and it's falling over time. The fact that the inverse function graph is also decreasing and concave down is related to that, but it's harder to understand and explain. Okay, I would challenge you to see if you can figure that out. So that's an example, a nonlinear algebra example of inverse functions. I do continue that in this section here, emphasizing the relationship with composition, as I talked about in section 1.8. When you compose a function in its inverse, you get back the original input. So here, f inverse of f of t does equal, well, t in the end, because t is greater than or equal to 0. You should always remember the square root of t squared is actually not equal to t in general. It's equal to the absolute value of t. However, t here is assumed to be greater than or equal to 0, and so therefore the absolute value of t does equal t. If t is actually less than 0, then its absolute value is negative t, which is actually a positive number in that case, but don't worry about that. The computation for f composed f inverse is done here, and we get back the original h, at least if we're not getting a square root of a negative number here. We don't want any imaginary numbers in this application. and we're assuming h is between 0 and 490. Okay, so these functions undo each other. All right, the next section is about inverse functions in general. This section is kind of abstract, but it's really, really important. You want to work at understanding abstract things if you want to understand what things are all about in linear algebra. So I've got the official definition, first of all, of what it means for a function to be one-to-one or injective. Here, I have talked about one-to-one and onto in previous sections, but I've never really given you an official definition. Here is a definition of one-to-one or injective and an example. Okay, I would encourage you to work through that. Here is the definition of onto or surjective and an example as well, and you can see it's related to inverse functions as I talk about here. And I talked about restricting the domain or codomain, and that's some subtleties you want to pay attention to. And in this section, this is probably the hardest abstract section, but again, it's real important. When your function is both one-to-one and onto, so f has a domain equal to a here and a codomain of b. If it's one-to-one and onto, that's called a bijection, then you can define an inverse function. Now, if it's not one-to-one or onto, you can sometimes restrict the domain or restrict the codomain to make it one-to-one and onto. But don't worry about that here. We are assuming in this section that the function is one-to-one and onto. And here's the key thing. Here's how you define the inverse function right here. Given an element little b in capital B, let f inverse of little b be the unique element in capital A that gets mapped to B. Okay, and that's a little confusing. You got to really think about that. First of all, why is there a unique element in capital A that gets mapped to B? That's because f is a one-to-one and onto. The fact that f is one-to-one means there's some element in capital A that gets mapped to B, and the fact that f is one-to-one means it's unique. Okay, and that means you can define it. And because of that, that means that the undoing facts are true. This fact right here is true, as well as this fact right up here. Okay, now it takes some real careful thought to really understand exactly what I'm saying here. I don't want to take the time to explain it. Okay, I think it's a good exercise for you to really work at understanding this. Sometimes drawing pictures, A over here, B over here, and drawing little a and little b back and thinking back and forth will be helpful here. This is also a couple hard paragraphs here. What I'm trying to emphasize is that function composition, first of all, is a binary operation. And with respect to this binary operation, inverse functions are kind of like multiplicative inverses of numbers. Okay, I talk about how f inverse of f and f compose f inverse give you identity functions, just like with non-zero numbers when you multiply a and a inverse really being 1 over a, the reciprocal of a, you get 1, the multiplicative identity for numbers, just like IA and IB are called identity functions or identity mappings, okay? So this is certainly confusing sometimes, but really make sure you understand it before you go on. Now we're getting into linear algebra and thinking first of all in this section about reminding you about what matrix multiplication is and how it's related to function and composition. Here again being the key equation, you want the matrix multiplication to be defined to match the function composition. So this section is just review, and based on this review, in order for S and T, when you compose them, to have a chance to be inverse functions, their matrix and A and B to be inverse matrices, these matrices and these functions and these domains and codomains have to all have the same dimensions. M, L, and N all have to equal each other in order for there to be a chance for S and T to be inverse functions and for A and B to be inverse matrices, okay? So we're talking, as far as the matrices go, square matrices where the number of rows equals the number of columns. Before we get into looking at how to calculate the inverse matrix for an invertible linear transformation, I do mention here also the basic application that we'll look at in more detail with some examples, that inverse matrices allow you to solve infinitely many problems. T of x equals b for any b. You can solve for x, okay? And if t is invertible, in other words, if a is invertible, that answer is going to be a inverse times b. That's the use of inverse matrices. If you can find a formula for a inverse, multiply it times an arbitrary b, you have solved this equation for any arbitrary b. So as I often do, let's start in low dimensions and work our way to high dimensions. This section is meant to be the easiest section, but it is kind of confusing when you look at it. If you looked at previous sections, you understand here that we're talking about 1-by-1 matrices being equivalent to numbers. Here's your arbitrary linear transformation. We're wondering what conditions on A will make this invertible. Well, it's pretty clear that A just can't be equal to 0, the number 0, and the inverse function is this thing right here. And in terms of matrices, you can write it this way, and you can compose these functions to confirm that's the inverse function. And like I said, if A is 0, this is non-invertible, and A is invertible when A is non-zero. That's the main thing to get out of here. All right, what about the inverse matrix of a linear transformation from R2 to itself? This is more important section in terms of generally what happens in linear algebra. And in this section, it's pretty nice. We can come up with a nice formula for A inverse. But I want to tell you how to derive that formula in a way that is going to be useful and generalized to higher dimensions. So we'd like to find, so if A is this 2-by-2 matrix representing the linear transformation T, we want to find a formula for A inverse if it exists, okay? And I talk about this equation being, well, first certainly obviously true, where this thing is called the 2-by-2 identity matrix, where you have a one's along the main diagonal and zeros elsewhere. And I talk about the properties of the identity matrix here related to inverse transformations and matrices. And the key equation you want to use to solve for the inverse matrix is this key equation right here. You want A times A inverse and also A inverse times A to equal I to the 2-by-2 identity matrix right there. And that equation can be written in this way. If you multiply the matrices on the left, you get this. And this is in order for this to be true, you get a system of 4 equations and 4 unknowns. You want to think of A, B, C, and D as being given, fixed numbers that are known. And you want to think of the alpha, beta, gamma, and delta as being unknowns. Those are what we want to solve for. So those are the unknowns in the system of 4 equations. This system is decoupled, also known as uncoupled. And so it's really equivalent to 2 systems of 2 equations and 2 unknowns, where here I took the first and third equations for this one here, and for the second one here I took the second and fourth equations. Okay? Solve this system for alpha and gamma, solve this system for beta and delta, and you found the entries of the inverse matrix if it exists. So what you do is you end up using row operations to take what I call a doubly augmented matrix and reduce it to reduced row echelon form. You could do RREF operations on this matrix and this matrix separately for both of these 2 cases, keeping in mind the variables names are different. However, again, it's more efficient to put this column and this column in the third and fourth columns of this doubly augmented matrix. Doubly augmented because I've added 2 columns to it. The third column with a 1 and a 0 represents the left-hand sides, or the right-hand sides of this first system, and the fourth column, 0, 1, represents the right-hand sides of the second system. And notice this is the I2. This is the identity matrix, in a 2-by-2 identity matrix. That's what I talk about here. We can represent this in what's called block form in this way. So you do the row operations to try to solve essentially both systems at once, and here are the details. I'm assuming in these details that I'm never dividing by 0, just for the sake of not worrying about that. You should double check these details. The last step is, depending on this calculation, it's the trickiest step here. And you can solve for alpha, beta, gamma, and delta. You get these things here, and that means the inverse matrix is this, as long as AD minus BC is not 0. And I guess looking at these, what I did up here, as long as A is not 0. However, I do mention here A actually can be 0. You'd need to modify the steps if A were 0, but you would get the same answer in the end. The key thing is AD minus BC cannot equal 0, and we've seen that quantity before. It's called the determinant of the 2-by-2 matrix. And so that what that ends up meaning is A is invertible if its determinant, if and only if its determinant is non-zero. And here's the formula for the inverse function, right? The inverse matrix down there, okay? As long as AD minus BC is non-zero. You should check the answer by multiplication. You can now, this scalar that's out in front of the matrix can be ignored at first, and you see that you get this matrix, which looks like the identity matrix, except it's AD minus BC instead of 1s along the diagonal. So we divide by that scalar to get I2 as desired. And ultimately, we also have this theorem that we can summarize what happened here, that a 2-by-2 matrix is invertible if and only if its determinant, AD minus BC, is non-zero, and because of this, the linear transformation is invertible if and only its if its standard matrix has a non-zero determinant. I haven't mentioned what a standard matrix means. That'll come out in chapter 2. So you might wonder, are there unstandard matrices? And there in fact are, and that's why I put that word in there. This section is about using the inverse matrix. Again, we can solve infinitely many problems at once. Here's your arbitrary system of 2 equations and 2 unknowns. U and V are arbitrary. We can think of this in matrix/vector form. As long as the determinant is non-zero, we can write the inverse matrix in there and write our solution in this way. And that can be checked in the abstract with these equations. This confirms that A inverse B is a solution of the system AX equals B right here, just substituting A inverse B in place of X. And this calculation down here confirms that it's the only solution. If AX equals B, then X must in fact equal A inverse times B. That guarantees that ultimately this solution is unique when A is invertible. If A is not invertible, well, you either get a consistent system or an inconsistent system. If it's a consistent system, there's actually going to be infinitely many solutions. We move on to the 3-dimensional case, inverse matrix of a linear transformation from R3 to itself, invertible linear transformation. I've got 2 examples, an invertible example and a non-invertible example. So here's the invertible example. I talk about how we want to solve for your inverse matrix in terms of 3 systems of 3 equations and 3 unknowns. 1, 0, 0, 0, 1, 0, and 0, 0, 1 are the right-hand sides. And you do a triply augmented matrix where you put those columns on the last 3 spots there, and you do reduce row echelon form. I do not show the details here because they're kind of unpleasant, but you should work through those details yourself to get this answer here. And that ultimately you write these things as columns of your inverse matrix. Here they are. You should double check all this. And here's a multiplicative way to check that this is the answer for the inverse matrix. Here I multiply everything out, and I get I3, the 3 by 3 identity matrix where you have 1s along the main diagonal and 0s elsewhere. And you could confirm this the other direction as well, and you get the same thing. And here I use the inverse matrix in the arbitrary case where I've got U, V, and W on the right-hand sides, and the answer again in general is A inverse times B. Here's the multiplication. You should check all this. Here's a non-invertible example, and it's kind of a funny non-invertible example. If we're feeling not very creative and we make our matrix be 1, 2, 3, 4, 5, 6, 7, 8, 9, it actually, amazingly, turns out to be non-invertible. That wouldn't be something you'd necessarily expect, but it is the case. And the reason that it's not invertible is because if you go to reduced row echelon form, what's on the left here does not end up being the identity matrix. You have a row of zeros for the first 3 columns here that represent the variables, the unknowns, and you've got non-zero numbers over here. And what that really means is you get inconsistent systems. For the third equations that result when you do the row operations, you get 0 equals 1, 0 equals -2, and 0 equals 1, which are contradictions. So that means when you do the derivation, assuming there's a solution, you get a contradiction, so there is no solution. A here, this matrix is non-invertible. That means this linear transformation is also non-invertible. And like I said a minute or 2 ago, that means your arbitrary system is either consistent or inconsistent, depending on what the right-hand side vector B is. If it is consistent, there will actually be infinitely many solutions, but I haven't proved that. Turns out the kernel will be more than just the 0 vector, and the image or column space is not all of R3 because the linear transformation is not 1-to-1, and it's also not onto. That turns out to be the case. Notice the dimensions of the domain and codomain here are the same. You might wonder, is there a determinant condition for 3 by 3 matrices? And the answer is yes, there is a determinant condition. Determinants for higher dimensional matrices get much more complicated. Actually, my last section of chapter 1, what I'm planning to be my last section, the next one, section 1.10, will be about determinants in general, especially 2 and 3 dimensional determinants, focusing on some geometric interpretations of determinants. Determinants actually can be a beautiful thing. I will talk about higher dimensional determinants as well, but not in as much detail as you might get in an actual hardcover textbook. Here is the formula for the determinant of a 3 by 3 matrix. I'm not explaining this formula, okay? This is the determinant, and here is your determinant condition for invertibility. Once again, the 3 by 3 matrix is going to be invertible if and only if its determinant is non-zero, and that means a linear transformation from R3 to itself will be invertible if and only if its standard matrix has a non-zero determinant. Again, I'm not explaining where this determinant condition comes from, but you could certainly check it on for yourself for examples. In fact, in referring to our examples, for the first example that was invertible, the determinant is non-zero, and the second example, the determinant is 0. Okay, so that confirms, at least for that example, this theorem seems to be the case, but I'm not proving this theorem. All right, what's the general algorithm for finding the inverse matrix? The reduced row echelon form of the augmented matrices, the double and triply augmented matrices, is what you generalize to find A inverse. So there's 3 issues to consider. If T is invertible, first of all, is T inverse really even a linear transformation? I was really assuming that earlier. How is A inverse found? And is there a determinant condition? Yes, there is a determinant condition. We'll look at that in a little bit more detail in the next section. For one, the answer is yes, it will be linear, but verifying that, again, I was really assuming that earlier, is trickier than you might think. You need to use the linearity condition, which I've also called the operation preserving condition. You need to prove this equation is true, where A and B are arbitrary scalars and U and V are arbitrary vectors. And you need to use the fact that T and T inverse undo each other, and T is 1 to 1, okay? And the line of reasoning is what you see here. This equation comes from the fact that T and T inverse undo each other. This line right here, well, the first equality is the fact that T is assumed to be operation preserving. It's linear. And the second equality here comes from the fact that T and T inverse undo each other in both of these spots. And what we have here then is that this equation is true and this equation is true, and notice the right-hand sides are the same here. Therefore, this equals this, which I say down there. And now the fact that T is 1 to 1 implies that their inputs must be the same. When you've got a 1 to 1 function, when the outputs are the same, the inputs must be the same, and that's the final conclusion, which is exactly what we want to prove. So that's an abstract proof that the inverse function, which will exist when the function is 1 to 1 and onto, is in fact linear. It's operation preserving, which again I was assuming really earlier. Here's the algorithm in general for finding the inverse matrix. You form your block augmented matrix, where the thing on the left is A and the thing on the right is IN, where N is an arbitrary positive integer. And you go to reduced row echelon form. If the block form of the result is in this form, then A is invertible, and the inverse matrix will be the matrix on the right that I'm calling B here. If in fact the block form contains a row of zeros in the n zeros in the first n columns somewhere, so one of the rows in those first n columns is all zeros. That doesn't mean that the numbers on the right side are 0. The last n columns, then A is going to be non-invertible. If you can't get an IN here on the left, that's what I'm trying to say. This method's justified ultimately by the same kind of reasoning with those special cases. Finally, here's our visual example. We're talking about a rotation of 90 degrees counterclockwise around the origin. Here's its matrix. Its inverse matrix evidently will represent a rotation clockwise 90 degrees around the origin. It should make intuitive sense that those kinds of operations will undo each other, and in fact that is the case. And here's your visual. You've got the original set here, the butterfly curve that's in red, that's A, which is R inverse of R of A. The blue set there is the image R of A, but the original set, the red one, is also the image of the blue set under the inverse transformation. That's what I'm trying to say. You can certainly think of this also as a 270 degree counterclockwise rotation, but that's less natural. You should also think about the fact that the inverse of shear will be another shear in the opposite direction, and the inverse of a reflection will actually be itself. And you might want to check that for particular examples of reflections. I only have a couple exercises so far, but I'm sure I'll add more. Thanks for watching.